Hello, today I'm going to talk about classification problem and logistic regression algorithm. So first we'll talk about the classification problem. Classification problem is given an input of x and get output of y in discrete values. An example of classification problems are, uh, for example, email spam. Is this email a spam or not spam? Uh, tumor evaluation, giving a tumor size of X, is this tumor malignant or benign? So the output of output of Y uh, can have only two values, 0 or 1. In this case, we call this as a binary classification problem. Y is either 0 or 1. If y can be multiple values, such as 0, 1, 2, 3, then we call this problem a multi-class classification problem. So now we know what is a classification problem. Next, we're going to talk about an algorithm called the logistic regression algorithm, which is widely used in binary classification problem. So the logistic regression is a learning algorithm for an input of x. We are getting the output of y as either 0 or 1. So it is a binary classification problem. So the logistic regression algorithm has the following steps. First, we calculate z equals to wx plus b. Here the w and b are the parameters. Next, we calculate the probability of y equals 1 for a given input of x. So we use the sigmoid function to calculate the y height, which is a sigmoid function of g, which equals to 1 over 1 plus e to the negative z, which z is in step 1 defined as w times x plus b. So the one important property of sigmoid function is the result of the sigmoid function is always between 0 and 1, like this graph is showing. So that's why we use the sigmoid function for the logistic regression algorithm, because we want to get an output always between 0 and 1 as a probability. So once we use the sigma function to get y height, the next step we will define if y height is bigger or equal to 0.51, and then we say y is equal to 1. So we give the prediction of a positive value for this problem. Else, if the y height is less than 0.5, then we say y is equal to 0. So we give a negative value for this prediction. So now we know the logistic regression algorithm. Next, we will need to talk about the logistic regression cost function. So the logistic regression is used to make a prediction of y height for a given input of x. So given a training example of multiple training examples like x1, y1, x2, y2, and up to xm and ym. So we want uh, to have the result of this logistic regression so that the y height I is close to y. Here the I means the ith training example. So we want our prediction of y height to be as close as possible with the ground truth label y. So in order to measure how well our prediction is doing, so we define a loss function as L of y height and y. So the goal is to have this loss function as small, the value of the loss function as small as possible. So like we make our prediction value as close as possible to the ground truth label y. So the loss function for the logistic regression is defined as follows. The L is equal to minus y times log y height plus 1 minus y times log 1 minus y height. So we use this algorithm to calculate the loss function for logistic regression. So again, the loss function, we use loss function to measure how well we are doing on a single training example. But in some cases, if we make a good prediction on one training example, but if the next training example we use the same function, but we make a very bad prediction, then that means this is not a very good algorithm. So we not only need to measure how well we're doing on each single training example, we need to measure how well we are doing on the entire training set, x1, y1 up to xm, yn, for the training set with a set for m. So we need to find a way to measure how well doing we are on the entire training set as a whole. So because of this, we come up with the following function. We call this as a cost function, J of with the parameter of W and B. So we define this cost function as 1 over n times the sum of all the individual loss function result, L, y height, and y. And if we take the equation of L and put here, then we get this equation for the cost function. So this is the cost function is a function of the parameter W and B. Remember in the previous slide, so the y height is a function of G, which is a function of W and B. So the cost function J is also the function of the parameter W and B, which are called the cost of parameters. So in order to know how to calculate this J of W and B, the goal here is to find out the parameter W and B to minimize J of W and B. So that is the goal of the cost function. So in order to achieve this, we need to first understand what is gradient and gradient descent. So first we need to understand what is derivative and partial derivatives. So derivative is the slope of the function f with respect to variable a, and it's defined as the height and the width. So in order to solve this, let me draw a function. For example, function, I say fa equals to 3a, and the axis is the a, and so this is the function. So what is the derivative? What is the derivative? Derivative is the slope of this function with respect to the variable a. So in this example, Let's say we have a equals to 2. Let's say we have a here. Right? In this example, so if we nudged a to the right a tiny bit, and fa will increase 3 times. Fa will increase 3 times as much. So the derivative for fa, right, so the derivative for fa at this point is 3 because it increases 3 times as much. So the notation is dfa with respect to parameter a. So in this case, the fa function only has a single variable a, right? So this is how we define the derivative. So derivative is the slope of the function fa with respect to a variable a, and which is the we can visualize it as the height and width for the function. So if the function has multiple variables, the slope of the function with respect to a particular variable is called a partial derivative. So in the first example, we only have one variable a, and then the slope of function is called the derivative. So if let's say if we have two variables of this function, j of w and b, right? So the slope of the function with the respect to a particular variable w, then this is called a partial derivative with the respect to variable w. And a similar case, we can write jwb and over the partial derivative b, which is the slope of function with respect to a particular variable b. So some functions like this even have the same derivative everywhere. I say 3 fa equals 3a, so it has the same slope everywhere. And some functions may have different derivative at a different point of function. For example, a function like this, we will have a different derivative, the different slope at a different place. Right? Yeah. So that is the derivative and the partial derivative. So once we understand this, we can talk about gradient descent. So gradient descent, to just recap, the goal is we want to calculate the prediction y height using the sigmoid function y height equals to wx plus b. And we define a cost function j of w and b as 1 over n with the sum of all the loss functions y height I and yi, where y is the ground truth label. So the goal is we want to find out the w and b that minimize the cost function j of w and b. So gradient descent is the algorithm or is the way for us to find the parameter w and b that can minimize the cost function j over w and b. So to run gradient descent, we will carry out the following update repeatedly. So in each iteration, we will calculate the w and b using the following algorithm. So w equals to w minus the learning rate alpha times the partial derivative of function j of w and b with respect to variable w, and b equal to b minus the learning rate alpha times the partial derivative of the cos j with respect to the variable b. So if we keep running this algorithm, we will eventually find out the parameter w and b, which minimize the cost function j. So just give an intuition about how gradient descent is working. Okay, so for example, we have this function. For example, we have this. This is a function of j of, let's say we only have one parameter data instead of two parameter w and b. Let's for simplicity of sake, let's say we only have one parameter data. So we have parameter one parameter data and the cost function of j of data. So at a different point of data, we have a different cost j of data. So the goal is we want to find out a parameter data where it minimizes the cost function j of data. We want to find parameter data at the local minimum here. So the way a gradient descent works, you can start from anywhere in this graph. Let's say you start from here. So every time you run gradient descent, you will get another value of data going towards this direction of finding the minimal value of j of data. So next time when you run gradient descent, you will get another data value somewhere here going towards the local minimum of j of data. So if you continuously run the gradient descent, you will eventually locate the variable data here, which has the which minimize the cost function j of data. So that is the intuition of the gradient descent, how gradient descent works. Here we also talk about learning rate alpha. So learning rate alpha controls how big a step we take on each iteration of gradient descent. So back to this example, let's say if we start from here, if our learning rate alpha is very small, then next time we will get a value we take a baby step for the next value here. Then if we run gradient descent again, we will get another value here, right? So it's keep going down, but it will every time take a baby step. So the result of learning rate alpha very small is the gradient descent algorithm can run very slow. So how about if the learning rate alpha is too big? So if we have learning rate alpha too big, let's say we start from the first one here, then the next one you may get a value here. We go from here all the way to here. And the next time it may shoot to here, the next time shoot to here, but the next time it may overshoot, come back to here, and overshoot to here. So if your learning rate alpha is too big, so you may overshoot the minimum, and you may fail to converge. So that is the gradient descent algorithm and the learning rate alpha. So again, to summary with the gradient descent, we can, if we run gradient descent enough time, we will eventually find out the parameter W and B, which minimize the cost function of J so that our logistic regression algorithm can make the best uh, prediction for the input of X. So, so that is the lecture today. Thank you.